We have already discussed how we can describe data if we know that it is bell-shaped. Well, not all the time is it bell-shaped. For instance, whenever we're talking about right-skewed data or left-skewed data, or those that we're not really sure what the distribution looks like. In that case, what we'd use is what we call Chebyshev's inequality. It's another way of computing the approximate number of data or percentage of data that is between two numbers. So you'll notice for any data set, regardless of the shape of distribution, so this works even with normal, at least this many or this percentage of observations will lie within k standard deviations of the mean. K just tells me how many standard deviations. Recall back with the bell-shaped, we talked about 1 standard deviation, 2 standard deviations, 3 standard deviations. However many standard deviations that is our K. And what we're going to do is we're going to take 1 minus 1 divided by K squared. We get that number and we're going to multiply that by 100%. That tells me how many data values, or the percentage of data values, that lie between those two values. You'll notice that it says that K has to be greater than 1. That means we're looking at more than 1 standard deviation. Part of that is because if I do 1 divided by 1, or even 1 divided by 1 squared, that's 1. 1 minus 1 is 0. So let me come over here and I'll do the calculation. If I had this, okay, then I would have 1 minus 1 squared is 1. And so I get 1 minus 1 divided by 1 is 1. So if I try to do this calculation, it's telling me that 0% data values lie within 1 standard deviation. So I can't really use this if it's just looking at 1 standard deviation. Let's look at an example. Using the data from the previous example, use Chebyshev's theorem to determine the percentage of adults that have an IQ score within 3 standard deviations of the mean. Well, maybe I don't know that the previous data, the IQ scores, were bell-shaped. So what I'm going to do is I'm going to use 1 minus 1 over 3 squared. And I'm going to multiply that by 100. Well, 3 squared is 9. So I get 1 over 1/9 times 100. When I'm subtracting fractions, I have to get common denominators. So I'm going to have a 9 over 9 minus 1/9 times 100. 9 minus 1 gives me 8/9 times 100. Well, 8/9 times 100 is going to give me 88.9%. So at least 88.9% of adults have an IQ score within 3 standard deviations of the mean. Since we know that this particular data is bell-shaped, the bell-shaped says that 99.7% of our data is within 3 standard deviations. Well, this statement right here, at least 88.9%, agrees with that. Okay, so it's not saying that only 88.9% fall within 3 standard deviations. It's saying at least that many. Determine the actual percentage of adults that have an IQ between 70 and 130. So 70 is 2 standard deviations from the mean. 130 is 2 standard deviations from the mean. We're going to use Chebyshev's just in case it's not completely bell-shaped. So we're going to do 1 minus 1 over 2 squared. times 100. 1 minus 1, 2 squared is 4. You will notice that I'm squaring before I do that division because I'm following the order of operations. I've got to get common denominators here. So my common denominator would be 4. So 4 fourths minus 1 fourth times 100. This is 3 fourths times 100, which tells me 75%. So at least 75% of adults have an IQ score between 70 and 130. Again, at least, because this is talking about 2 standard deviations, bell-shaped 2 standard deviations would be 95%. Now we've been looking at the mean. We've looked at the variance. We've looked at the standard deviation. What we'd like to do now is what we call the coefficient of variation. The coefficient of variation, and let me write this down so that I can concentrate, of variation, tells how large the standard deviation is relative to the mean. What we're looking at with the coefficient of variation is, comparatively to the mean, is this standard deviation a large or a small? We use this to compare the spread. Are things more spread out or are they closer together? When we look at 2 separate types of data that don't have the same units, we want to compare them. Well, we can't compare their mean. We can't even compare their standard deviation. What we can do is we can compare their coefficient of variations, because their coefficient of variations have gotten rid of the units. And it's just telling me, relative to the mean, how spread out is the data. This is talking about maybe IQ versus age, or income versus years of experience. Those things do not have the same unit, and so we compare them using the coefficient of variation. So let's look at an example. So the National Center for Health Statistics study states that the mean height for adult men in the U.S. is 69.4 inches. So we have the height, and the mean is, and I did that incorrectly because we're talking about the population overall, and the population mean is 69.4 inches with a standard deviation of 3.1. So sigma is equal to 3.1 inches. The mean weight for these same adults, the mean weight is 194.7 pounds with a standard deviation of 68.3 pounds. Well, we can't compare this 3.1 to the 68.3 to see which one's more spread out. What we're going to do is we're going to use the coefficient of variation. CV is equal to the standard deviation divided by the mean. So we first want to compute the the coefficient of variation of the height. So the coefficient of variation, we're looking at the height. We're going to take the standard deviation, 3.1, divided by its mean, 69.4. And if you look at the units, inches over inches, notice what happens to the units. They cancel each other out. They divide out. So coefficient of variation has no units to it. Whenever I divide these, I get 0.0447. Now I'm going to do the same thing with weight. I'm going to find its coefficient of variation. So that's 68.3 pounds over 194.7 pounds. And again, the units will divide out. And I take 68.3 divided by 194.7. And I get that the coefficient of variation is 0.35. These two, this is telling me that they're spread out by a little over 4%, about 4.5%. This one is saying they're spread out over 35%. So the weight actually has a greater spread. So again, the weight has a greater spread relative to its mean. We're talking about how spread out something is. Which one has a larger spread comparatively to its mean? Again, I can't compare 68.3 to 3.1. I can guess that weight has a greater spread, but I'm not sure because maybe the mean weight, or I'm sorry, the mean height is a lot taller. And that would actually change my coefficient of variation. So whenever you're wanting to compare things that have different units, you need to use that coefficient of variation so that you can see which one has a greater spread. So I'd like for you to practice some using Chebyshev's theorem, or Chebyshev's inequality, and the coefficient of variation. If you have questions, please let me know.